Next topic is induced electric field. Okay, from the beginning of the chapter we have discussed a lot about induced EMF, induced current. Now obviously when there is induced EMF and induced current, there will be induced electric field also. So now we will discuss about that. See, suppose if this is a coil and a galvanometer, if a magnet is moving towards it, obviously there will be change in magnetic field, there will be change in magnetic flux, and there will be current in this, and there will be EMF. So here there will be electric field also. In this case, here the magnet is stationary, but this coil connected to galvanometer, if this is moving, definitely there will be change in magnetic field, there will be change in magnetic flux, there will be induced EMF, induced current, and there will be induced electric field also. So relative movement or relative motion or relative movement will cause what? Will cause induced EMF, induced current, and induced electric field also. Okay, so this we have already discussed. We have seen Faraday's experiment and all, and the direction of EMF, direction of current using Lenz's law, everything we have seen. Now we will spend some time to understand about induced electric field. Suppose if this is a conductor, if it is kept in magnetic field, okay, this is magnetic field. Now suppose if this cross magnetic field is increasing, the direction of magnetic field is in this direction into the board. Now if that magnetic field is increasing, what will happen here? This will try to decrease this cross magnetic field, so that what will happen? This is going to induce dot magnetic field here. So if dot magnetic field come in this direction, obviously it can oppose this increase in cross magnetic field. So induced magnetic field will be in this direction. So this is going to be the current direction, that is anti-clockwise. Anti-clockwise current will be there. Anti-clockwise current will be there. Clear? Anti-clockwise current will be there. So all of us know this. Okay. Now what will be the, first we will see what will be the direction of electric field. Okay, if there is a positive charge, that positive charge will move in the direction of electric field. Since the direction of current is this, the direction of electric field is also in this direction. If it is circular, then this is going to be what? Tangential. This is going to be the direction of what? Electric field. If we consider this point, this will be the direction of electric field. This is the direction of electric field. Clear or what? Okay, so because of this electric field, actually this current is generated here. Okay, clear? So this is the direction of electric field. This electric field, the speciality of this electric field is, this induced electric field is not due to charge distribution, not due to charge. This electric field is not because of electrostatic conditions. This electric field is due to change in magnetic field. The reason for this induced electric field is due to change in magnetic field. So I could say that induced electric field is due to change in magnetic field. due to change in magnetic field. Okay, so not due to charge or distribution of charge. Okay, clear? Induced electric field is due to change in magnetic field. Clear? Fine. Okay, note it down. Pause the screen and note it down. Okay, clear? So this is not due to charge or distribution of charge. This is because of change in magnetic field. So we can say that whenever there is change in magnetic field, whenever there is change in magnetic field, electric field will be induced. Electric field will be induced. So direction of electric field will be what? Direction of electric field will be based on the Lenz's law only. Okay, based on whether dot magnetic field is increasing or cross magnetic field is increasing or decreasing, based on that we will find induced current. So that induced current direction only the direction of electric field. So direction of electric field is the direction of what? Direction of electric field is same as the direction of current. Direction of electric field will be same as the direction of current. Clear? Note it down. Clear? Suppose if we are taking a conductor, okay, a closed conductor in the magnetic field, and suppose if this magnetic field is increasing, okay, this is increasing, so it will try to make dot magnetic field. The clockwise, anti-clockwise current will be there. Suppose if I decrease it, if this magnetic field is decreasing, this one, what will happen? It will try to increase cross magnetic field. So this is the direction the induced magnetic field will be. Current direction is going to be clockwise. Clear or what? So current direction will be clockwise. Okay, now suppose if we consider a point P here, so current will be there, current flow will be there, charge motion will be there. Suppose if a charge here, if it is moving in this direction, okay, this is moving in this direction at a point P, a charge Q is moving in this direction for a length dl, so this is a positive charge, and this charge is moving for a distance dl, okay, at a point P. So what all force will be there with this charge? If the charge is moving in this direction, due to magnetic field, there will be a force. What will be the direction of that force? If this is the direction of charge motion, if this is the direction of field, this is going to be the direction of magnetic field. Magnetic force. This will be the direction of magnetic force. If this is the direction of magnetic field, this is the direction of charge movement, this is going to be the direction of magnetic field. Now, what will be the direction of electric field? There will be electric field in this which direction? There is going to be electric field in this direction. Suppose if we consider this point, the direction of electric field is this. So we can say that there will be electric field is in this direction. So electric force, what is electric force? In electrostatics, we have studied electric force is what? Electrostatic force is what? QE. Okay, charge into electric field, QE. So here there will be tangentially, there will be electrostatic force also. Okay, clear? Clear? So work done by magnetic force will be what? 0, because the direction of displacement and magnetic force is 90 degree, but the direction of electrostatic force and displacement is 0 degree. They are in the same direction. So suppose if I consider the small work done for moving this charge for a length dl is nothing but electrostatic force dot dl. The work done by electrostatic force, or the overall force, even if we take this, will become work done due to gravitation. Magnetic force will be 0. So I am considering electric force only, Fe dot dl. Now suppose if I divide both side with the charge q, what will happen here? dw by q, and this is equal to what? Fe by q dot dl. What is dw by q? That is work done by charge is what? When we have studied current electricity, one definition and one problem based on this we have done. The definition of EMF was the work done to take a charge through the closed loop, closed path is what is EMF. EMF is the work done to take a charge to move the closed path. Entire circuit, closed circuit is what is EMF. We have studied there. Okay, so I am using here. So work done by charge is nothing but the small EMF dw by q. So I am, instead of writing E, I am writing dE. What is this? Fe is equal to QE. So Fe by Q is what? Electric field. So I could say this is E dot dl. Now if I need total EMF, I need to add the work done for all the circuit. From where to where? From this point all the way back to this point. So I am writing here. So E is equal to, that is EMF is equal to what is total dE. This is equal to, I can put integration. Instead of writing 0 to L, 0 to X, I am integrating from this point to the closed path. So I am putting here closed integral. So closed integral of what? E dot dl. So I got here EMF is equal to what? Induced EMF is nothing but integral E dot dl. Now from Lenz's law and from Faraday's experiment, we have already studied E is equal to what? Minus d phi by dt. So I will be writing here minus d phi by dt. So this relation is important. So using this relation, okay, we will be able to find the induced electric field also. Okay, using this relation we will be able to find induced electric field also. Okay, so we will do, when we do problems, things will be clear. How to find electric field from this concept we will understand. Okay, pause the screen and note it down, children. Clear? Okay, so now we will do some problems based on this. Okay, so that we will understand like how to find induced electric field also. Okay, clear? Okay, now we have seen about induced electric field. What will be the direction of induced electric field? How to find induced electric field using which concept? E is equal to closed line integral of E dot dl, which is equal to minus d phi by dt. Execution, how to implement that and find the electric field, we will see in problems. Now certain important things, okay, important points regarding induced electric field is, okay, already I have mentioned, but I am summarizing this. Okay, this induced electric field is due to change in magnetic field, Okay, number 2, induced electric field is not due to charge or charge distribution. Not due to charge or charge distribution. Okay, clear? Now induced electric field is not electrostatic electric field. Induced electric field is not electrostatic electric field. So the force, okay, due to induced electric field is not conservative, not conservative. We have seen electrostatic force is conservative, while work done against electrostatic force will be stored as what? Potential energy, electrostatic potential energy, all these things we have seen. But this electric field, induced electric field, is not conservative. Important point. Why this is not conservative? Suppose if we take E dot dl is equal to minus d phi by dt. Suppose if you multiply charge here, this is nothing but, this will become what? Force. Q into E will become what? Force. So work done for a closed path, okay, please note it down. I shall explain this again. Okay, please note it down. Please note these points. This I shall elaborate this point. Clear? Pause the screen and note it down. Okay, now what is the relation involving induced electric field? See, closed integral E dot dl is equal to minus d phi by dt. Now when we multiply with the charge on both the sides, we will be getting QE dot dl is equal to minus d phi by dt into Q. Now if it is a conservative force, okay, if this is a conservative force, the work done, Okay, in the closed path must be what? This must be 0. But in the closed path, force F dot dl integration, that is work done in taking the charge, just like if we take like this, the work done from here to here, the closed path, is equal to what? Minus d phi by dt into q. This is not equal to 0. Some value is coming here. That is why we can say this is not conservative. Not conservative. Important point. Please note it down. Okay. Pause the screen and note it down. Okay, children. Now we will do some problems on induced electric field also. Okay. See, students, another small topic is eddy currents. So eddy currents are loops of electric current induced within the conductor by a changing magnetic field in the conductor. Suppose if we have a conductor here, okay, this is a plate, not loop or something, but a solid disc like something. So if the magnet, if we take a bar magnet, if we bring it towards it or away from it, definitely what will happen? There will be induced EMF and there will be induced current. Okay, so we have seen like induced electric field, we have seen induced electric field, same thing will happen here. So there will be induced electric field and that will be in circular path, and there will be induced current also, that also will be in circular path. So suppose if we consider suppose if this is a conductor, okay, so this conductor, this is not a ring or something, this is solid conductor. So here if we bring magnet to and fro, definitely there will be current inside this. So what this is in the shape of eddy. Eddy means whirlpool, right? The whirlpool of water. So just like rotating current that will be formed here. That is what is eddy current. Okay, so pause the screen and take it. Clear? Okay. Now we need to understand this eddy current can cause damping. In oscillations, in simple harmonic motion, we have seen about damping. Same thing will happen here. Suppose if we keep north pole of a magnet here, and if this is south pole, suppose if we are just like here, like just like outside and inside, okay, just like if we draw okay, if we draw like this, then if this is a pendulum, okay, if this is swinging inside and outside, so suppose if this is swinging inside and outside like this, then if this is north pole and south pole, that is what I have tried to show here. So what will happen here? So when it is coming, the magnetic field is moving like this. Okay, so if it is increasing, if it is entering the cross, okay, anyway, whatever it may be, the magnetic field will be increasing. So there will be induced current inside this that will be trying to decrease the magnetic field. So when it is coming inside, if it is coming inside, there will be what? Repulsion. There will be repulsion. Okay, when it is going out, what will be there? Attraction. So the eddy current will be formed here, eddy current. So this eddy current, when it is trying to come, it will repel. When it is trying to go, it will attract. So this will cause what? Damping. This will cause damping. So this will slow down the eddy current slows down the what oscillation, okay, which is called damping. Clear? Please note it down. Okay, pause the screen and note it down, children. Okay, then what is the disadvantage of this eddy current? This will heat up the conductor also. Okay, eddy current heats up the conductor. Okay, suppose so say if this is a body, okay, this is 3D, okay, three-dimensional body. So when there is eddy current, this eddy current is going to be everywhere. Eddy current will be throughout, three-dimensional flow of eddy current will be there. So what we are doing is we will slice this, okay, we will slice this like this, okay, we will slice and insulate this. What we will do, we will take the conductor and we will slice it. We will cut into different pieces and we will insulate this, and we will use, so that instead of having this three-dimensional eddy current will be there, but it will limit like this, So heating, what is heating? I square RT. So if we can reduce eddy current, okay, heat can be reduced. Clear or what? Okay, so eddy current is this, it will heat up the device or conductor. We will slice it up and we will laminate or illuminate it so that we can reduce the eddy current, so heat will be reduced. Clear or what? Okay, children, so that's all about the induced electric field, and eddy current is also an application of that. Okay, fine. So we will see in another session. Goodbye, good luck.
Hello students. So now we are going to do some problems on induced electric field. Okay, problems involving induced electric field. Okay, the whole chapter is about induced EMF, induced current, okay, all these. In between, now we are discussing about induced electric field. Okay, induced electric field, the formula, okay, which we learned about giving the relation between induced electric field, EMF and all, is nothing but E is equal to line integral, closed line integral of E dot dl. This is equal to minus d phi by dt. Okay, now by doing problems we will understand like how can we use this formula. Okay, so let us move to the question. Okay, so this is the first question. If the inward magnetic field is decreasing, which of the following best represent the induced electric field lines? So generally we have studied in electrostatics, that is electric field and charges, that this electric field lines are not closed lines. This electric field lines used to be like what? If this is a positive charge and if this is a negative charge, from this positive charge electric field lines will emerge and this will end at a negative charge. We don't get any closed loop here. Suppose in magnetic field, if we consider magnetic field, if this is north pole and south pole, see from north pole the field lines will emerge in the outer side of the magnet. In the outside the magnet, the field lines will emerge from north pole and they will join in the south pole. But inside the magnet, this field will be moving from south pole to north pole. So this is actually closed line. This is closed, but this is not closed. So that is the reason you can look at C and D. They are not closed lines. So obviously, if our target is on electric field lines, we will have a temptation to mark either C or D. But there should be there should be a clarity on whether that is positive charge or negative charge and all. Okay, general case. But here in this question, we are focusing or we are discussing about induced electric field lines. So dear children, induced electric field lines are closed ones. Okay, already we have discussed in the theory. Suppose if we keep a conductor, okay, so if we keep a conductor like this, okay, just like given in the question, okay, if we keep a conductor like this, okay, if the inward magnetic field is decreasing, if this B is decreasing, then the induced magnetic field will be in which direction? Induced magnetic field also will be in the crossed direction. I mean, which is going to go inside. Magnetic field directions will be into the paper. Correct. So in order to have into the paper, we will have the current in the clockwise direction. So this is going to be the direction of induced current. This is going to be the direction of induced current. Now, while studying the theory, we have studied that if whatever way the direction of current, that is the direction of electric field. This E is what? Electric field. So in this case, we are having clockwise electric field. So, but these are closed ones. So here you can take a note that induced electric fields induced electric field lines are closed ones, are closed lines. Clear or what? So option A is the answer here. Option A is the answer here. One more, the concept which we need to understand from this question is induced electric field lines are closed ones, but the electric field lines due to charges or electrostatic electric field lines will be what? They will not be closed lines. Clear? So be very precise and clear on this. We will move to the next problem. Okay, so this is the next problem. What they are asking is a square non-conducting loop. Non-conducting loop this is. Okay, 20 centimeter. Okay, on a side, 20 centimeter. Okay, on a side is placed in the magnetic field. The center AB coincides with the center of magnetic field. The magnetic field is increasing at the rate 2 Tesla per second. The potential difference between B and C. The potential difference between B and C they are asking. Okay. So how to do this problem? Okay. So here certain data they have given. Okay. One data is like this magnetic field. Magnetic field is decreasing at the rate 2 Tesla per second. So dB by dt is what they have given here. 2 Tesla per second. Okay. Now suppose this magnetic field is increasing. If this magnetic field is increasing, then what the induced magnetic field will do? The induced magnetic field will try to decrease this. Okay, so if they try to decrease this cross magnetic field, what will be the induced magnetic field? Induced magnetic field will be dot magnetic field. Okay, so I could say, suppose if we draw this, okay, this the magnetic field induced will be what? Dot. Okay, here if I consider this square, this is going to be a dot. Induced magnetic field will be dot. So induced magnetic field is dot, means the direction of current will be what? Anti-clockwise. So I could say that the current direction will be what? Anti-clockwise. Anti-clockwise. Okay. So now, what will be the direction of electric field? The direction of electric field for this segment, this is the direction of electric field. Suppose if this is D, C, B, A. For a BA, the direction of electric field is this. Okay, here for AD, direction of electric field is this. For DC, the direction of electric field is this. Clear? Now let us apply our formula. Okay, let us apply our formula. That is, the EMF is equal to what? Closed line integral of E dot dl. E dot dl. Now here, the electric field is constant. Electric field is constant. Okay, electric field will be constant everywhere because same current is passing through this. Okay, now if we try to integrate this, electric field we can take outside because that is going to be constant, and this line, closed line integral of dl, if we do, okay, so E dot dl means integral EDL cos 0, because dl means nothing but this length of this conductor. Length of this conductor for AB, for ED, for DC, for CB and all. Okay, the length of the conductor, current carrying conductor, and electric field is in the same direction. So I have written cos 0. Now E I have taken outside, closed line integral of dl we are doing. Okay, so suppose if this each length is, suppose if we consider A, this is going to be E into what? 4A. Line integral of dl for a square is nothing but that perimeter of that square. So E into 4A. Okay, so let it be there. So this is the EMF. This is the EMF. Okay, now electric field value we do not know. Length of the loop, one side we know, that is 20 centimeter. We'll come to that. Now EMF E is equal to what? Minus d phi by dt we know. So this is equal to minus d by dt of B dot A. B dot A. So now here the magnetic field direction, and area vector direction, we can take it as same, in the same direction. So this is going to be d by dt of BA, or we can say A we can take outside. Area is not going to change. So minus A into d by dt of B. So d by dt of B they have given in the question. How much? 2 Tesla per second. 2 Tesla per second. So now area is what? Minus A square into 2 Tesla per second. Clear? So this is again EMF. Now equating it, electric field into 4A is equal to minus 2A square. Now this square and this A if I cancel, and this 2 if we cancel, we can say that electric field E is equal to what? Minus A by 2, or this is equal to minus, what is the side? Side is given as 20 centimeter. So 20 into 10 raised to minus 2 divided by 2. So this is going to be minus 10 into 10 raised to minus 2. Okay, now what we need to find? We need to find the potential difference between B and C. So the potential difference between B and C is what? E dot L, E vector dot L vector. Okay, or potential difference is what? Electric field into length. So my just we need only mode. So 10 into 10 raised to minus 2. See, in the options that we can take only values. So I am writing 10 into 10 raised to minus 2 into length is 20 into 10 raised to minus 2. So this is going to be what? 20 millivolt will be getting 20 millivolt. Clear or what? So option D is the correct answer. Option D is the correct answer. So children, I will discuss this question once again. They have given a cylindrical, okay, what? A cylindrical loop where magnetic field is there, which is increasing. They have kept a non-conducting loop there. Okay, this loop is non-conducting. So we need to find the potential difference between B and C. So how we will find the potential difference? So for that purpose, we are finding the EMF using the formula line integral of E dot dl. So we got E into 4A. Then EMF is equal to d phi by dt. Change in magnetic field is given. So using that, we found again another formula for EMF, that is 2A square. Equating these two, we got electric field. Potential difference is electric field into that length. So we got the potential difference between B and C, or whichever length they ask, we can find it like this. Is it clear? So this is how application of induced electric field can be used. Okay, so this is one question. Shall we move to the next problem? Yes. So next question is like the magnetic field within a cylindrical region whose cross section is indicated starts increasing. Whose cross section is indicated start increasing. That is, the magnetic field starts increasing at a constant rate alpha Tesla per second. Magnetic field is increasing. The graph showing the variation of induced field with the distance r from the axis of the cylinder. Okay, so in the options, I would like to add one more thing. Just like here, we can add the radius of this cylinder. Actually, we should, for proper clarity, the radius of this cylinder, if we take as r, here we can add r. Okay. Okay, now let us verify the behavior of induced electric field, okay, for various situations. So one first case, okay, we will take first case, that is this r, that is distance from the center, is inside this cylinder, inside the cylindrical region. That is, if we take the cylindrical region, magnetic field is there, magnetic field is there. Now from the center, a point we consider, this is inside the region, this is inside the region. So here we will put r. Clear? Now how to find electric field? Let us take the formula. So this closed line we will take, this closed line we will take. If so, then EMF is what? Closed line integral of E dot dl. E dot dl. Now here, this is closed line integral of E dl cos 0, cos 0, or we can say E, if we take outside, this is integral of dl. So EMF will be equal to what? E into 2 pi r. E into 2 pi r. So that is one method of finding EMF. Another method is what? E is equal to minus d phi by dt. Okay, so this is equal to minus d by dt of ba cos 0. This is equal to what? Minus of what? B is changing here. So A, if we take out dB by dt. So this is equal to what? A is what? Pi r square minus pi r square of this marked circle. Okay, so here again, here also magnetic field is there, but we have taken a point inside. Okay, pi r square into what? Alpha. Pi r square into alpha. dB by dt is given as alpha. So now if we equate E into 2 pi r is equal to what? Pi r square alpha. Pi r square alpha. I am just ignoring the negative sign. Okay, we are not going to find out the direction and all here. So r if we cancel, then electric field is what? Electric field is equal to pi also will be cancelled off. Electric field is equal to r alpha by 2. R alpha by 2. So from this, we can understand that electric field is directly proportional to R. Electric field is directly proportional to R. So from this itself, we can say that option B is wrong. Option D is also wrong, because directly proportional means straight line. So only possibility is A and C. Now let us see what is going to happen outside. Okay, let us take outside also. Now second case. Okay, second case is nothing but outside, that is r greater than the radius. Suppose here this is the cylindrical region where magnetic field is there. We have taken from the center, we have taken here, we have taken r. So this is the okay loop we have taken. Now again same formula. If we try, E is equal to line integral of E dot dl. E dot dl. So if we consider E outside, line integral of dl if we take, then E into what? 2 pi r, just like the previous case. Okay. Now another formula is what? E is equal to d phi by dt. Okay, mod E. Okay, here this is also E. This is also E. Okay, so d phi by dt. So d by dt of what? Ba. If we take A here, this is going to be d by dt of B. What is area here? What is the area here? So area where, if this is capital R, area where this magnetic field will be there. Magnetic field is not there outside R. So this area I will have to take as what? Pi r square. I will have to take pi r square into alpha. So if I equate this, E into 2 pi r is equal to pi r square alpha. If I take like that, this pi and pi will be cancelled off. I will be getting E is equal to what? R square alpha divided by 2r. Here this capital R alpha 2, everything is constant. So here E is inversely proportional to what? Capital small r. So this shape will be like this. Shape will be like this for inverse proportion. So what will be the graph we can take? So the graph is going to be option A. Option A is matching exactly for inverse proportion. So option A is the correct answer. Okay, so here this is straight line. First case E is proportional to R. First case. Second case E is inversely proportional to R. So if we draw the graph, if we draw the graph, how it is going to be? This is going to be first till the radius. Okay, this is R and this is electric field. Till the radius it is straight line. After that, this is going to be having this relation. This is R. Clear? So option A will come. Hope you understood. Okay. Next problem. Okay. So here a magnetic field B is equal to 2t cube minus 24t is present perpendicular to the plane of disk of radius r as shown in the figure. The direction of induced electric field at a time t is equal to 2 seconds. Okay, so what is that? Line integral of E dot dl is equal to minus d phi by dt. Okay, what we need to find? We need to find the direction of electric field at a time t is equal to 2 seconds. Okay, so this is equal to what? A into dB by dt. Okay, so line integral of E dot dl is equal to area into d by dt of 2t cube minus 24t. So minus a into this is going to be 6t square minus 24. 6t square minus 24. So putting the value of time, this is going to be 6 into 2 square minus 24. So this is going to be what? 0. This answer is going to be 0. So what will happen? No electric field will be induced in this case. So option C is the correct answer. Clear? So based on induced electric field, few problems we have done. Okay, so practice well, understand the concept. Okay, then okay, so try to practice more number of problems and be comfortable in this topic. Clear, children? Okay, so let us wind up this session also. Thank you. Goodbye. Good luck.